Welcome to the NPTEL course on storage systems. Today we will start discussing a bit about reliability, especially for future systems. Okay. I have given some information I picked up from multiple sources, and for example, it is believed that currently we have about 100,000 nodes in some large systems, okay. And this is slightly old information, because for example at Stanford University recently somebody used 1.5 million nodes to do some computation. We have a rocket which is going up, it makes a lot of noise, right. So there is a highly nonlinear systems that operation at the time when the gases are going out, how to reduce the noise, okay. And somehow they use some 1.5 million nodes to do some computation to figure out how to reduce the noise that is generated, okay. We can see the issues that are there when you think about such systems. If there is some minor errors here and there, can they corrupt the whole, let us say, result that you finally depend upon, right. How do you know that some particular nodes, they are not doing the wrong things, okay. It could be for multiple reasons. It could be because of the code itself is wrong, or it could be because the hardware is generating errors which is not predictable, and basically because I mentioned to you, you can have memory errors, disk errors, HBA errors, network errors, all those kind of things. So we are talking about 1.5 million of these guys. How do you trust what is coming out? Okay, that's a big issue, okay. So again, the concurrency levels also are going to be heavy. This in terms of million, they are talking about 1000-fold. Like you can see that already these numbers seem a bit old, okay, because as I told you already in 2012 they have done 1 million, okay. So not clear, this is just some information I picked up from some presentation, okay. And if you look at the DRAM, we are talking about 4 petabytes now, 10, 30, 60 petabytes, okay. It's huge amount of data, okay. Now what is interesting for us is the following here. What is the mean time to abort? That is, if you start some computation, how long does it take before a system dies? Okay. That is, you have to restart the system. You can see that it's 1 day supposedly now, and it's going to become 1/4 of a day. That means it barely works for 6 hours, then it will die, okay. Now you can see why these things are not slightly difficult things to work out. Why? If it is taking 1/4 of a day and dying, it has, in the first place, you might have to store, you may want to checkpoint what has happened as you are going through, right. And if you have 60 petabytes, this 60 petabytes have to be written somewhere. Where will it be stored? It has to be stored most likely in the storage system. Now ask yourself, how long will it take to store 60 petabytes? Okay. Now if we assume disks, then it's a hopeless task. 60 petabytes on disk will be just genuinely hopeless. But if you have things like SSDs, this may be feasible, okay. Basically just can think about it. Usually you find that a disk will give you about, nowadays, okay, we can assume 1 gigabit per second approximately, okay, or 2 gigabits per second, okay. So if you talk about 60 petabytes, we are talking about 10 to the power of 6 approximately more, 10 to the power of 6, okay. We are talking about 10 to the power of 6 seconds approximately, or somewhere in the region, 10 to the power of 5 to 10 to the power of 7 seconds. That is already a good part of the year, okay, from a few months, okay, almost a month or something like that. So you really have to change your storage system systematically, okay. You have to ensure that you need your SSDs which will have at least 2 or 3 orders of magnitude higher bandwidth. Then you can start thinking about checkpointing it. What is, I think all of you, I hope you are all familiar with checkpointing. What is checkpointing? It's basically a way in which you do some computation, you know that something bad is going to happen. So at some regular intervals, you save the state, so that if that bad stuff happens, you can restart from there. That's basically checkpointing, okay. So our issue now is that checkpointing is going to be highly storage intensive. Every time you are going to checkpoint, you have to write it to some persistent storage, basically storage system, and you have to start thinking about that. Okay. So this is going to be a big issue. Okay. Other issue is there's a similar thing with respect to storage system alone, and they say that this is luckily 14 days, etc. Storage application visible interrupt. Okay. Basically something that is going bad in the storage system and you can detect it. This happening because of some other errors, typically in memory, CPU, communication, wherever. Okay. Because there are so many of them, you have something like more than 1 million nodes and you have a 1 billion level of concurrency. Okay. These are all stupendous numbers. Okay. And so we are concerned about a correctness, what we are doing, and the question is, there is a correctness that the storage can give you, but other systems may not be able to do it at the same level. Okay. So that's the reason why there is a difference between 1/4 of a day and 14 days here. Okay. Because these systems are much more well engineered with respect to error management. Okay. A good example is that when you do anything with a disk, for example, you have for example a CPU, you have a host bus adapter, and you have the disk. Every single jump from one to the other, there is somebody checking things. Okay. Nobody can, you cannot write from CPU directly to disk. The HBA is sitting there and checking things. So there are multiple levels at which any error is caught. Okay. But this has to be done more systematically, and that is where the big issue is. Again, let's look a bit about some other reliability data. If you look at what is called bit error rate, BER, consumer SATA is e to the power minus 14, okay, 10 to the power minus 14, and enterprise SATA is 1 order of magnitude better. If you go to what is called SCSI attached storage and fiber channel, it's even one more level better. There is something called, this is a tape, it's one particular technology of tape, LTO. You can see this is really 3 orders of magnitude better than SATA. Okay. The reason why these are, let's say these are so good is because for a long time, you want, if you want to really save something for the next 10 years, 15 years, tape was the only medium. Okay. And so there has been a lot of stringent restrictions on the, let's say, the specifications for these tapes, because they are the long term storage in some sense. Okay. And you notice that even movies and all these things are used, typically stored using tapes only. Okay. So this LTO is basically a very good quality system, and it is typically guaranteed also that if you store it, I guarantee 10 years that tape will not go bad. Okay. It will be available. Okay. Whereas if you look at CDs and DVDs, you know that oftentimes they go bad within 1 year. Okay. Because I think I must have mentioned it some time back. Typically there are some dice used, and the dice, if they degrade, then you lose a bit. Okay. So again, what is more interesting is that these are errors that you can catch. Right? There is some error correcting code, something somewhere sitting there which is actually catching it for you. Okay. I think we already discussed something called latent sector error, where you try to read a sector and the system tells you something is bad there, and that is basically this kind of data. There is even worse things called undetectable errors. Okay. And you will see that in SATA it is 10 to the power of minus 17. That means that if you have a system with about 100 petabytes, okay, you are going to have at least one undetectable error. We don't know where it is going to hit. Okay. Depending on where it hits, it may be calamitous or it could be something minor, nothing to worry about, right, where it hits. Okay. It's like, for example, your injury in the brain or in the toe. Okay. Probably the injury on the toe you can easily handle, but for injury in the brain you can't handle, something of that kind. Okay. So you can see that there are various technologies. It turns out Ethernet is really, gigabit Ethernet is really very well designed, because they have additional levels of protection in the headers, okay, in the Ethernet headers. Okay. And so essentially you can see the channel error rate is this much for everything, because they use the same fiber optic cable essentially. Okay. They are using equivalent of that all over the place. Okay. The same medium, but different coding methods have been used. That is why you will find different kinds of let us say rates of undetectable errors. Okay. And okay, I made a mistake here, this should not be here. Okay. So okay, so you will see that if you take fiber channel and this thing and use some additional protection, okay, we can go all the way to 10 to the power of minus 28. Okay. We will discuss this briefly today, this part of it. Okay. So, this is almost rock solid. Okay. We are talking about, you need to have about 1 trillion petabytes or more, okay, before you start worrying about this problem. Okay. So, this is on a stupendous scale. Okay. So, this I think is good enough, absolutely good enough, we can really depend on it, but this is going to be expensive because we are talking about fiber channel or SCSI attached storage. Okay. So, let us given this background, I think you should be clear about there are certain types of errors that can be detected by your error coding. These are this, that is a bit error rate, and there are some which just cannot be caught, okay, because your error coding technique is very good, but still it has certain points in the coding space which do not result in an error being signaled. Okay, that is basically the problem. So, what are the kinds of problems we have? Essentially, since we are in the storage business, the data corruption is a big problem. Okay. So, where are the problems? It could be magnetic media. Typically, you use something called Reed-Solomon codes. Typical thing is about some 40 bytes or so will be used to handle 512 bytes of sector. Okay. It also could be, there could be errors because of drive firmware. I think all of you know that firmware is also some piece of software, right? It is just that it is being done, let us say, at a level much lower than you normally see. Okay. And this also is some piece of code. So, there is no way to write perfect code, and therefore, you can also make mistakes here. Okay. So, it could be that you asked it to write a particular place and somebody made a mistake in the firmware and some peculiar condition, right, where instead of n it became n plus 1 or I and I minus 1, whatever, the standard kind of off by 1 errors. It could be writing in the wrong place. For example, somebody could be saying write to track number 77 and the drive firmware makes it 78. Okay, that is possible. Also, other thing is when the data, when it travels from one place to another place, there could be problems. Okay. So, typically when you send out data, right, you are not within, you have to amplify the signal, okay, and you send it out, but there is also a lot of noise outside. Okay. So, if the noise is, it is not shielded, suppose it is not very well shielded, then you get into problems where the bit can flip. Okay. So, then you have to make sure that when you send it from one place to another place, somebody has to have certain types of let us say summary information by which you can figure out if what you are getting, something is wrong with it. Okay. And this is often called CRCs, cyclic redundancy checks, or for example, in IP networking you have something called IP checksums. Okay. So, this basically in some sense what you are doing is you have some checksum, you make the checksum travel along with the data. On the recipient side, you look at the data, compute the checksum again, see if the checksum is the same as what has been sent to you. Okay. If they both are same, then you know that at least there is some chance that it is actually correct. There is a good chance it is correct. Okay. Because there could be some pathological case where the checksum and the transmitted checksum, the computed checksum and the transmitted checksum pathologically do some interesting things so that they come out to be right, even if there is an error. That is also possible. Okay. But that happens so rarely, they do not have to worry about it. Okay. So, because that is a very rare case. Okay. Of course, software errors, okay, that also is possible. Okay. So, there are various errors and we will look at some of these parts of it. Okay. So, how do we handle these things? You use, if you are talking about servers, they use RAID, I think we discussed it briefly. Basically, you compute a parity across multiple disks and use that as a way to see if one of the drives fails, then you can recover the data from the parity, for example. Okay. Same thing with system buses, they also have parity, and again this is something which has to be done across the whole system. If you are having ECC in the memory, you should also have ECC in the cache also. If you have ECC in the cache, then you have to ask yourself, should I have ECC on the registers also? Okay. If you only have it at a particular point, then it may not be sufficient. Okay. So, it has to be all through. Okay. sometimes people will decide that as long as it is safe in the cache, and it may not be necessary to have ECC on the register contents. Okay, I think that's how it is done. I don't think there's ECC in the registers. Okay, but you have to design very carefully, thinking about it. Suppose I don't have it, can I get into a problem? And engineers or people who design these things think carefully and say that the chances of happening are so low that I don't have to worry about it. Okay, that's how it is done. Okay, basically it is, the errors depend on the volume also, how big the data is. So buses typically have protective measures. For example, you have an ALU bus, you may want to ensure that that ALU bus actually has some parity. Okay. In addition, if you take advanced file systems, like for example, there is one in Linux called BTRFS, or there is one with Sun had come to ZFS, they have checksum on data as well as metadata. Okay. But the big problem has been that everybody is doing their own little thing for error management, but there is no overall scheme which actually handles all of it. What is called end-to-end integrity from one side to another side. For example, pick it up from the storage side, it is traveling from storage to HBA to network to various things, right? I need to ensure that the whole path is protected, not just one part here and there. Okay, that is basically what is called end-to-end integrity. Okay, now there are some standards have come up. There is something called data integrity field diff for the storage stack. There is a extension. This is not actual standard as far as I know. This is for above the stack. If you use both the diff and dix, then you are mostly covered. But this has been standardized, this part. There is a what you call a standards body which has actually gone ahead and standardized this one. This I think is still in the, let us say, people are using it, but it is not part of a standards body as far as I know. Okay. So how does this work? Okay. So there is an end-to-end protection standard. It is there is a technical committee. Some American National Standards Institution has got some committee. Okay, and the T10 is basically the one which handles storage. Okay, and what they have done is, for if you have they attach for every data block 512 bytes, they attach a data integrity field of 8 bytes. Okay, just like your ECC also, right? For every 32 bits, you add 7 bits of ECC, right? Something like that. Okay. And if you look at the diff itself, it has got, because it's 8 bytes, right? So basically 512 plus 8, 520 bytes. So the new sector is 520 bytes. Okay. And of this 8 bytes, there is a reference tag, meta tag, and guard. Okay. So basically the guard is basically the one 16-bit CRC of sector data. Okay. So basically if you read the data and then you compute a CRC, the data has some CRC value and what you read CRC is different, then you know something is wrong. You read the sector wrong. Okay. Now that is a part of that is 2 bytes. There is one meta tag which is left unpopulated, so that any OS can decide what to do with it. It is just extension, so you can left for future use. Okay, or any clever guy who knows how to use it well. Okay. Then there is a reference tag, which basically is that it is a 32-bit number used to ensure individual sectors return into right physical sector. Okay. Basically, what you do is the following: if I am trying to write a sector, suppose I am supposed to write a sector 47. Okay. So you put 47 in the reference tag and write it. The fact that I said write to 47 doesn't mean that somebody down below, he actually wrote to sector 48, right? But luckily for me, it goes to 48 and clobbers something in 48, fine, okay, it's sad. But luckily for me, the data will still have 47 as the reference tag. When somebody reads it, right, that guy is reading to, he is going to sector 48. He reads it, but the reference tag says 47. Then I know that something is wrong. Is this clear? Basically the idea is the following: you always try to describe where the data should be. The data is supposed to go to sector 47, but by some horrible mistake somewhere down below the stack where I am operating, it actually went to sector 48. Okay. So, but luckily for me, it has gone to sector 48, but the reference tag is what I set it. It it has, because I am sending everything in one shot, okay, the data plus this diff part, and that one still has 47. Since it has got 47, when I read it next time, I went to sector 48, but the data says it is actually 47. Then I know that something is wrong with this particular sector. Okay, so that's how you can catch some errors, and these are considered to be quite not exactly rare. People have discovered there are faulty devices in the system which have a tendency to do some of these things at various points in time. Okay, okay. So again, these kind of errors you might think are slightly strange, but you will start seeing in many devices which you commonly use. For example, some of you might have noticed that if you go to any high-end cameras, right, they also have firmware, and the firmware nowadays you can download firmware into your camera because it has the bugs in it, okay, because it's doing something wrong, it's doing some color equalization, whatever, it's doing various things, they're all algorithms, okay, and it could be that some of it is wrong, okay, wrong in mostly correct, but there are some minor corner cases where it gets wrong. So again, the firmware has to be downloaded to fix the problem, okay. Even the lenses, for example, turn out to be managed by certain firmware, okay, and you might get into some difficulties if the firmware is wrong. And so basically what we are talking about is there is a lot of firmware all over the place, and the firmware can do mistakes, okay, because some computation is going on and it is not going to the right place. So basically what is the how do you use this diff? I mentioned that the host bus adapter, which is basically a proxy for the CPU, right, it calculates a checksum value for the data block and writes, stores it in the DIF. So basically the data is there and it stores it in DIF, okay, and this whole thing is sent out, and then the storage receiver gets it. It has got the diff that was computed by HBA and it has got the data, okay. Now it sees if the data that it has got, it will compute the checksum again on that one, only in the data, sees if it is what the diff it got from the HBA. If they both match, mostly it's okay, and then it stores the data plus checksum, okay. So on a read, for example, because it has stored the checksum also, you read the checksum, you get the data out of it, okay, and then you check the receiving HBA also checks it, okay. Now we are talking about diff, which is basically only the storage stack, so we are not talking about CPU side, okay, because that's the reason why it's only between HBA and the device, okay, that's only between that part, okay. So these are roughly it works, okay. So the real issue is the diff enough? I think already I mentioned that above the storage stack you need to do something also, that's why it's not enough, okay. So what basically the diff does is it prevents content corruption and misplacement errors. I already mentioned misplacement, instead of going to 47 sector it is going to 48, okay, and it protects path between HBA and storage devices, okay, but does not provide integrity for software stack such file system, okay. Now the file system itself is a fairly complex system. It's really can be extremely complicated because it is typically highly concurrent, and it is also not only talking to applications, it's also talking to the virtual memory subsystem, okay, and it is and it also, the file system also is quite complex precisely because it has to bridge the gap between memory speeds and disk speeds. So it has to do a lot of caching and various kinds of things like that, okay. So because of that, it turns out the file system also there could be some very subtle bugs, okay, and for example you can have bad buffer pointers, misdirected writes, all this also can happen, okay. So we need to provide, in addition to diff, some additional stuff. That DIX is basically that attempt, but as I told you, it has not been standardized. Let us just take one example of a error correction above this diff layer, okay. So ZFS uses what is called end-to-end checksum. Again, it's a file system, so it has no control over what is above it. So it can only do end-to-end from the point of view of starting from where it enters, the data enters into its system till it goes to disk and back, okay, till the point it goes back up again. That's all it can handle, okay. Whereas if you go for DIX, probably can go all the way to the application also, okay. Now checksum not stored with the data block, but in the pointer to the block, okay. That's one minor difference than what I said before, okay. Again, all checksums are done in servo memory, so it can catch various kinds of errors. Okay, it can catch phantom writes. Sometimes, as I mentioned, the write actually doesn't actually happen at all. Why does it happen? Because you are trying to write, and suddenly what happened was there was a big dust particle was sitting there. So your disk head, because of Bernoulli effect, it actually goes over the dust particle, and essentially the magnetic field that is used, it becomes so weak that actually nothing happens below. Okay, it's become a phantom write. Okay, so we already discussed misdirected reads or writes where disk accesses the wrong block. We discussed this already. There are also parity errors between storage array and servo memory, or storage array or driver. Okay, there are those kind of errors also. Sometimes you have the device driver errors. You are writing device drivers now. You know how you can make mistakes, right? So where data can be stored in the wrong kernel buffer itself. Of course, usually most of the systems we use have been tested extensively, especially file systems are tested extremely rigorously. Okay, because everything depends on a file system being correct. Okay, otherwise no work is possible. Okay, but in spite of that, there are bugs, and once in a while, some corner case which nobody ever expected shows up, and who knows, your data might be stored in the wrong kernel buffer itself. Okay, especially concurrency can get into these problems. There have been very unusual errors reported. For example, I remember in 96 or so, this Microsoft had a file system on the servers, and if you access a web page rapidly enough, okay, it will corrupt the data completely. Only if you access the web page very quickly, okay, that is, you are asking for information at a very high rate, okay, then in that case it turned out that it would corrupt the data. Okay, that's a fairly good explanation why it could have happened, but it's because of that corner case. Okay, and now it turns out that this error correction is not exactly cheap. For example, you need to process 500 megabytes per second kind of throughput, because so much data is streaming through, right? You need certain amount of CPU processing power. Okay, and essentially if you look at it, it's something like 1 cycle of CPU, right, for 4 bits IO, because somebody has to touch something, right, because basically you are doing checksum, all those kind of things. You can do caching, you can do all kinds of things. In spite of that, there has to be some cost associated with that, and essentially 1 cycle of CPU for 4 bits of IO. And this is a costly thing because in 1 cycle you could have done add, you could have done a 32-bit add, a 64-bit add. Okay, so what you are doing is, instead of doing one add of 64 bits, you are touching the IO bits, okay, 4 bits at a time, equivalent of that, okay, and we essentially expended that amount of CPU processing power to do it. That's the reason why most often if you are doing some of these things, oftentimes you need hardware acceleration, okay, and the hardware acceleration is understood in the context of encryption and decryption, but with this kind of stuff, I think it is still not much there. Okay, the only thing about ZFS error correction is that it's not based on any standards. Okay, it is done by Sun Microsystems there in their file system, and so all this stuff what we are talking about may not be available in other systems. For example, ext3 did not have it. ext4 has some basic checksumming going on right now. So ext4 is going to be somewhat more reliable than ext3, but it might not do some of these things. For example, ext4, I don't think it handles misdirected reads or writes. Okay, if it uses a diff for example, then possibly Linux can also do it. Okay, but if you want to make Linux ext4 handle misdirected reads and writes, you need to have diff, but that also means that you need support in the various layers in the system. Okay, for example, you have buffer cache. Okay, even the buffer cache now should actually start having these checksums. And what is more difficult is that anytime anybody does any mapping, for example, you have something called memory maps, right, M-maps, right. Now, M-maps basically are mapped to memory, and anybody can be changing any bytes. Okay, that means that any byte, anytime any byte takes place, any change in the byte takes place, somebody has to recompute the checksum again. As long as that is not possible, then the whole system is not trustworthy enough. Okay, That means that the only way you can guarantee this is if you use what is called direct I/O. What is direct I/O? Those things that do not go through the virtual memory subsystem. You are having some I/O which does not go through the caching mechanism of the virtual memory subsystem. Okay. Then it turns out that you cannot update those areas of memory through other applications or whatever, right, other threads or whatever activity, they cannot touch it. Because you are guaranteed that you are going only through only one interface which you can control, and therefore you can do all these things. Okay. So you can see that even if you are interested, the current models of memory map etc. will not allow you to do a good job of all these things. Okay. So you have to think carefully before you decide to do this. You have to fix all your interfaces before you can start trusting all these things. It will catch some errors, but there are quite a few errors it will still not be catching. And again, it depends. Suppose you have, we talked about 30-60 petabytes of memory, right? Now we look at the kind of ECC, that error correcting code that it has got. If it has got, let us say, much weaker error correcting code capability than what the disk is providing, then probably all this stuff what we are talking about is not useful. Somehow it has to be equal, approximately about the equal kind of capability. Your disk correction capability, error correction capability, and the memory error correction capability should be somehow matched. Okay. Then only it makes sense to take all this trouble. As I mentioned, you have to change a buffer cache, you have to change so many layers before you can get it working. Okay. Now, in top of this diff, as I mentioned already, you also need something so that application also can get some additional guarantees. So, disks basically, as far as it was defined by some people at Oracle, it defines a set of interfaces that host adapters must provide in order to exchange integrity metadata with the host operating system. Okay. So, basically the application calculates a checksum and passes it to the HBA, and this is appended to the 512 byte data block. So, in a sense, now application and HBA, they now understand each other, just like previously HBA and the storage device was understanding. So, now we have from the application all the way to the storage device and back. Again, this is, as I mentioned before, if there are caching is going on and there are threads which do not understand this part and they update things and do not update a checksum, you are lost, nothing is useful. Okay. So, you have to control that part also. Okay. So, if you take in those kind of, if you handle those kind of issues, essentially it provides a full end-to-end data integrity check. Okay. So, basically to provide this kind of protection, you have to have the controller has to be disk capable and the storage device also diff capable. Okay. Both the same. Okay. So, basically if you want to handle things with respect to integrity, there is a general mechanism, and as I mentioned, there are certain things which are done at the storage level itself. This guard, for example, okay, and the reference tag. These two things are typically used at the storage level itself. This is for misdirected writes. This is for just errors, to catch errors, CRC type. Okay. This meta tag is left to the OS or any layer above the storage. Okay. And the question is, what can we do with this? Okay. So, that is what we are talking about here. So, we can, there is a method called algebraic signatures that can be used to ensure integrity of data. Okay. Some small mistake here to ensure, I think I have repeated it twice. Okay. Use algebraic signatures to ensure integrity of both data and metadata. Okay. What is the useful property that is needed? If there is a big block, let us say it has got so many sub blocks, the property I am interested is, if you give me the signatures of the sub blocks, I can easily compute the signature of the whole block. In a sense, it is compositional. Okay. If you have that property, then I can do what I did before also. So, you remember what is happening here? If I look at this, right, what is happening when I do this guard bit? Basically, it is saying that if I have so many bits, I sum them, right, I do a CRC, okay, then the CRC that I get is basically based on each of the bits of the data, okay, it is basically depend on the data, it is compositional, okay, and because of that, when I send it across, other party also can compute using the same algorithm, using the same CRC check, okay. So, that is the reason why this whole thing works. So, the question is, can we do something similar at this level also, okay. So, basic idea is that come up with some notion of signature which captures something about the data, okay, like the CRC, so that it is compositional. I give you subparts, I should be able to compose the signature of the higher level entity, okay. I take the higher level entities, multiple of those guys across, again I can compute the signature of even higher level entity, okay. I have basically some kind of a recursive mechanism. If I have that property, everything works out. It turns out you need some special theory for this. We will not go into too much, I will just mention a few things about it, okay. And this is basically something called the field. I think you heard of rings, groups and fields, right. So, there is something called a Galois field which has got this property, okay. So, I am not going to great detail about this thing, I am just going to mention roughly how it is done, okay. So, usually in this Galois field, you have the number of elements is p to the power of n, where p is a 9, p is prime. It turns out that in this case, because we use binary system and p is prime, therefore 2 also is a prime, right, you know all that p2 is prime, therefore 2 to the power of n. So, typically we use GF 2 to the power of 16. And if you look at it, the various elements in this system are basically binary strings which can also be seen as polynomials, okay. And it turns out that addition, subtraction, equivalent to XOR, therefore they are commutative. So, I can say a plus b, okay, is same as b plus a, it does not matter which order I do it, okay. So, I can do it in any order I like, okay. And there are similar things that you can do for multiplication and division, okay. It turns out that to define this algebraic signature, I need something called irreducible element, okay. Basically, we are talking about in a field, it turns out that you can have multiple elements in this field, and some of the fields can be written as products of other elements. Just like you take our regular field, integers, right, you can write 6 as product of 2 into 3, right, whereas irreducible is similar to our prime numbers, okay, it is not a product of non-trivial factors, okay. So, it turns out that if you can get one of those irreducible element, then if you have that irreducible element, you can, it turns out that if you keep multiplying by itself, you finally can get to 1, okay, in this Galois field. This is not may not be really valid for our integer system, because we have, let us say we have unbounded integers, okay, then it will not happen in our case, okay. But in a field, for example, you have only 2 to the power of 16 elements, okay, in this Galois field. Therefore, it turns out that once you start multiplying by itself, finally it will come back to, it will become part of itself out of 2 to the power of 16. You can keep multiplying, but finally it will come back. So, there is some I for which it becomes alpha to the power I becomes 1, okay. This is what is called order. It turns out if you choose, if there is something called a primitive element for which order is basically s minus 1. For example, if 2 to the power of 16, I want an order of 2 to the power of 16 minus 1, okay, use that as a primitive element. If you have a primitive element of that kind, it will always be there for this kind of systems, okay, then it turns out you can define a signature like this, okay. So, basically you can define a signature as the following. What is signature? That is defined by, suppose I have symbols x1, x2, xn, okay. What will I do? If you want to get a signature for this particular alpha, okay, what I do is I do a sigma of each of these things, x1 into alpha to the power of 1 plus x2 into alpha to the power of 2 all the way to xn alpha to the power of n. Okay. Now, this is basically the signature. It turns out signatures have a very interesting property of this variety. Signature of alpha of x1 plus x2 is signature of alpha of x1 plus signature alpha of x2. What it means is that if I am able to compute a signature of, let us say I have x1 and x2, there are 2 blocks. Okay. I compute a signature on block 1, I compute the signature on block 2, and then I do XOR, because addition, I said, what did I say addition was, is basically equal to XOR in this game. Okay. So, when you do that, you can essentially, so I get the sub signatures, I can do XOR and I get the signature of the upper level, higher level, like the x1, these are 2 blocks, I concatenated, for example. Okay. So, that is one interesting property of this particular system. Okay. Now, other thing that is there, because you have a limited number, right, this 2 to the power of 16, elements are 2 to the power 16. That means that you could be dealing with very large things. You could be dealing with 4096 byte blocks. What is the space of possibilities there? 4096 bytes is 4096 into 8. How much is that? It is about 32,000, right. So, what is the number of possibilities in how many different blocks are there? How many different blocks are there for type, let us say with the data? It will be 2 to the power of 32,000 approximately. That is the number of possible ways you can fill up a 4K block. Okay. And so, it is a tremendously huge number. Okay. But finally, what we are doing, we are only handling it with 2 to the power of 16. Right, we only have 2 to the power of 16 codes possible, that is all that is there maximum, because we are talking in our signature is basically 2 to the power of 16, what is an element in 2 to the power of 16, g of 2 to the power of 16. Okay. So, when you go from 2 to the power of 32,000 and you map it to something which is only 2 to the power of 16, right, that means that there is a chance that you might get something by accident. Okay. That is what we are talking about here. Okay. So, then the signatures of 2 different sectors collide with the probability 2 to the power of minus f, where f is the length of each symbol. Okay. So, basically it is 2 to the power of minus 16. Okay. So, basically you are talking about the fact that since you have a much limited size signature, only 16 bits, okay, the chances that the 2 things will by sheer accident, by just simple accident are identical is 2 to the power of minus 16. Of course, if you feel that 2 to the power of minus 16 is too small, then you can go 2 to the power of, you take 32 bits, you get that higher number. Okay. So, what is the, why is it that this is, basic thing is that you are, you already have various methods of error correction, etc. on the system. Okay. Various parties are doing, I think as I mentioned, all these guys are doing various things, right. Your RAID is taking care of some problem, system bus are taking some problem, okay, various guys are doing various things. Now, we are putting on top of it this particular thing. Okay. Therefore, even if you think that 2 to the power of minus 16, okay, is not good enough, okay, it can create problems. But once you have all these things, you are slightly in good territory. Okay. That's the reason why you will notice this one. This is that T10, what we are talking about, protection. Okay. You are at 10 to the power of minus 21 without this thing, without this end-to-end correction. Once you put that in, it has gone to 10 to the power of minus 28. You have got now 7 additional levels or orders of magnitude better, let us say, protection with this kind of model. Okay. So, that can be mostly good enough for many purposes. Okay. So, again in engineering you do not go for the, the very best possible thing, because that is usually costing too much, you do not have the resources to do it. So, what you do is you incrementally increase it so that you are in safe zone, essentially, that is basically what you are doing. Okay. Okay. So, what do we do out here? So, the basic idea would be that you have signatures and they have this property, which is an interesting property, and it is same property like what we are doing with checksum also. Okay. And this is exactly also assumed in the case of IP checksums, for example, in networking also. Basically, you have a packet, you keep on doing the IP, you keep on every 16 bits, you do a checksum, and then you compute the checksum of the next 16 bits, and because of the additive property, you are in good shape. Okay. So basically, what we are doing is we will use these algebraic signatures on subblocks and blocks, because what's a block in a storage system typically? Let's say it is 4 kilobytes, but the hardware itself, the disk itself, it's happy with 512 byte sectors. Okay. So in a sense, your one block is equivalent to 8 sectors, and if you notice our design, the diff, right, it's doing at the level of 512 bytes, right? That's basically what we are seeing here, 512 bytes. Okay. So the thing is, we have to figure out what is the corresponding signature for the block. Okay. And that's one part of it. The other thing is that we also want to see whether if you have even longer thing, for example, the file is there. A file is, it can be 1 byte, it can be 100 bytes, it can be 10 gigabytes, one single file, right. That means that you have to find a way in which you can take each of these block by block, compose the signatures one by one till you get the signature of the whole thing. Okay. Now, of course, if you have something like a 10 petabyte file and there is a there's another 10 petabyte file, the number of times you do it is so high, possibly that it might not be worthwhile. Okay. It may be that it might actually be equal by some with a high probability. That's also possible. Okay. Unlikely, but probably that's a good chance. Okay. But if you are talking not on that scale, what you can do is you take the algebraic signatures on subblocks and blocks and you compose them in such a way so that you can essentially again check it just like previously you did with CRC. Okay. So what we need is we need a new signatures that summarize the production information over longer inter-sequence units such as blocks. For example, suppose I have a block Bn. Okay. So now this block is itself composed of multiple sectors. Each sector you get 2 bytes, right? That's basically what our design says. Okay. Each sector is getting 2 bytes. So if you have so many sectors, right? For example, in the case of a 4 kilobyte block, how many sectors are there? 8 sectors are there. So you take 8 sectors into 2, because you have essentially 16 bytes of information available. Okay. So what we can do with what can I do with the 16 bytes? I am going to say that I am going to take the 16 bytes and put some certain things will store the let's say I have 8 sectors, right. Let's say that I put some of the subblocks, right. I keep those things in the 16 bytes, but I also keep the integrity block of the next guy. So what is the idea? The idea is that when I read some stuff, I read 2 blocks and then I will check the correctness of not only with respect to what I have here, but also with the next one. Okay. In a sense, what I am doing is I am creating a system by which every piece of data is not only held to a certain standard with respect to consistency within itself, but also with respect to some information nearby. So if somehow there is some mistake somewhere, okay, you can catch it. Okay. So those kind of things also can be done. Okay. I'm just giving you some high level idea, but there are a lot of things that I have to work out, and as I mentioned to you, this kind of stuff will require amazing amounts of changes in your file system stack. I think you have some experience of looking at the file system stack. For example, this will essentially change your block layer, right. It will change your buffer cache, okay. It will change your file system, it will change your inode structures, it will change all these things, okay. Suppose somebody wants to design something of the kind, they have to go and change every one of these things, okay. So it's not something which most people want to think about. That's why you'll notice that these kind of designs are very good, very important, but it's not being yet seriously designed into systems that are there right now. Okay. So people are doing what is appropriate, that is, they will do it only at a certain extent, which catches most of the problems, and then leave it less, okay, leave it to the let us say. So that's why you will see this diff DIX. Diff has been standardized, DIX has not been standardized, because DIX means that now you have to worry about all these things, all the structures all the way from the file system all the way up. Because if you notice it, right, where do we stop here? We go only up to the HBA side, okay. Okay, we are only, if you use diff only HBA and storage wise, whereas if you want to go to DIX, you have to start thinking about everything from file system, and file system is again a very complex thing, database, all these guys are complicated things, everything has to change there, okay. So that's the reason why it is not common to see DIX etc. going on. Diff I think is beginning to become common, standard. Okay, so basically error management is going to become extremely important in future logic designs. I think I already mentioned the biggest problem that people see is when you have so many threads, so many let us say concurrent activities going on. If you want to contain the error, you have to actually find a way of validating the results as they are being generated, okay. And especially when you have something like 1 million nodes, they will be traversing networks and various things, buffers and this and that, right. And every time they are going through, somebody has to be checking the correctness of all these things, okay. And that's what makes it very difficult. I already mentioned you need amazing amounts of support across various components of the storage and application stack. I think file system is complicated enough, but once you go into database etc., there will be a lot of problems. For example, in the case of I mentioned file system, but also you can have things like volume manager, right. There is typically you will see that there is something called a volume manager which takes all these disks and makes it pretend as if it's a big one single disk. That also has to get changed. Then on top of it the file system has to change, then the libc has to change, then the application has to change, okay. Every one of these guys have to go take all this integrated information back and forth, and they have to update these things, and then there is a chance that you will actually have reasonable guarantees. But that turns out to be extremely difficult to do in practice. That's why you will notice that currently we have only the diff that is being done, because it is in a selected area where the errors are slightly on a larger scale. But if you talk to people in large scale systems like CRN, okay, they will actually be quite serious about using this kind of things, but unfortunately there is nobody to provide this kind of solutions even as of now, as far as I know. There is the standard way to do it is by engineering the components better and better, okay. So for example, disk bit error rate, for example, sometime in the past was 10 to the power minus 13, now they have gone to 10 to the power minus 14, you go to 10 to the power minus 15, and then if fiber channel disks are 10 to the power minus 16, okay. So now that's the typical way in which you are handling it. Basically you make each of subcomponents really very good, so you don't think about it, but when you are talking about a very large system, you have to think about it. There is no way to, there is no escape, okay. And that's the same reason why if you look at Google kind of file systems, they decided to go what is called spread out their systems rather than having extremely powerful machines in one single place. Basically what happens is that once you do it, you tend to be able to scale the systems. Again, you can, error management also has to scale appropriately there, and again Google kind of file systems, they actually have a lot of checksums all over the place, so that even if there is any error that you get from somewhere, right, you are able to recover. That's why you have 3 copies, right. So you can see all kinds of things there. ext3 will be doing its own error checking, the hardware will be doing it, the OS will be doing it, the network will be doing it, and GFS also will be doing it on top of it. So all these guys have to work together. Then only there is some chance that you get reasonably good let us say system that is operational. Otherwise you will get the situation where every 6 hours it will not work, okay, which is same as what used to be there in the 1940s. If you look at 1940s, they're extremely the components were extremely error prone, extremely error prone. So in the 1940s, when the computers were designed for the first time, your typical, let us say, mean time to failure was few hours. That is, you want to get some computation, you start it, and hopefully if your computation is within 3-4 hours you get a result, otherwise it will die. And then everybody had to check the results, you have to check whether this result actually is meaningful, okay. So there was all these complications those days. Finally we come to a situation where components are reliable enough that you can mostly forget about it, like in laptops, but if you go to high scale you still have to think about it, okay. Okay, I think I will stop here.